Great, thank you so much. Thanks very much for inviting me here, and it's great to be part of such an amazing session with all the other speakers. I hope you guys realize how lucky you are getting all of these messages of encouragement, and something I wish I'd been exposed to in my formative years. I'm going to talk about I guess, a bunch of stuff that I've done through my career and how I've gotten to be, I guess, an entrepreneur. It's the first time I've ever said that out loud today. I'm a little bit ashamed and embarrassed and excited at the same time. So yeah, I'm a professor at the ANU in physics, and I'm going to let you in on a secret, something else I've never told anyone before, that I'm not really that interested in science, and I never actually was that interested in science. I kind of got into physics because I like to wear shorts to work, which I can do if I'm a professor. But it turned out to be sort of a bit of a secret advantage that I had, and one of my friends commented that they thought that the reason that I work on so many different interesting things is because I'm so bored by a lot of the stuff that other people are doing. Like, I look at it and go, seriously, this is what you want to spend your life on doing? And it's great that people want to do that, it's just not for me. So it means that I've sort of cherry-picked the stuff that I thought was the most interesting to me, and had a lot of fun doing it. So let's get into it. So this is a couple of black holes. This is one of the biggest discoveries in astronomy in recent times. And they're two black holes far, far out in space, 1.3 billion light years away. And this is something that we saw a couple of years ago using a brand new way of looking at the universe. In fact, it's much more like listening to the universe. And it's using something called gravitational waves. Has anyone heard of gravitational waves? Wow. Normally I ask that question up until a couple of years ago, and there was just like crickets in the room. So that's great. And in fact, next week, one of my colleagues is heading to Stockholm to be part of the Nobel Prize celebrations. We won the Nobel Prize in physics. So in a very short time, with the publication of this paper, we went from being crackpots, like literally crackpots. People would review our grant applications and say, everybody knows these things don't exist. You're wasting your money, you're wasting your time. And now we're seen as visionaries of the field. So it's a really huge turnaround. This is the instrument that I've spent the last 21 years of my career helping to build. So these are two interferometers. It's a laser interferometer gravitational wave observatory. They're in the US, in Hanford and Livingston, on opposite sides of the country. And they're basically like big ears, and they're listening for gravitational waves. So I'll just tell you what gravitational waves are really, really quickly. So gravitational waves, if you think about light or radio waves, you can make radio waves by getting an electron, a charged particle, and wiggling it around in space. And then it shoots out electromagnetic radiation. Gravitational waves are basically exactly the same, except you have a mass. No charged particle, just a mass, and you wiggle it around, and it sends out gravitational waves. And these are ripples in space itself. So what they do, there's gravitational waves passing through us all the time, and what they're doing is they're moving us closer together and farther apart, but it's a very, very small effect. So small, in fact, that if we were to try and measure the change in the separation of the Earth and the Sun, they would get closer together and farther apart by less than the thickness of a human hair. So it's a really, really, really tiny effect, which is why it took us decades and decades to detect. This is how small it is. So this is an atom, like there's maybe 10,000 atoms across a human hair. We zoom in on the atom to the nucleus, go further and further and further, and the nucleus is really, really very small. If we zoom in on the side of that, this is how much a gravitational wave moved our mirrors by. This much. And that was a big gravitational wave. That's like the biggest one that we've seen yet. So it's really, really hard. And to do this, we needed to develop a whole bunch of different technologies, mostly using lasers and bouncing them off mirrors and having very, very long arms to be able to see these effects. This is a really interesting graph. This is actually not a scientific graph at all, but this is a graph that I like to show. And this is the number of downloads from the Physical Review Letters server around the time that our paper was published. So here, these are the number of page views per hour. It's going along like this. Physical Review Letters knew that we were going to come out with this big paper, so they actually bought 4 new servers from Amazon to host the paper at the time. And then you can see this spike here where it was actually 10,000 downloads per minute of our paper when it came out. And it crashed the servers, so they doubled the number of servers. It crashed it again, and then they doubled it a third time, and it finally could deal with it. So this is a really kind of important graph about impact of that work, that so many people worked on it. It was myself and 1,000 of my closest colleagues all working very hard to make this discovery. Only about 2 months ago, we saw a completely different source, nothing to do with black holes at all, but these are two colliding neutron stars. And well, there's a bunch of really interesting things about this. It was the first time that we saw light come out at the same time as gravitational waves. There were 65 telescopes all pointed at the right part of the sky because gravitational waves we heard them, we said, we think it's over there somewhere. All the telescopes pointed there, and we saw a whole bunch of stuff. it solved a big mystery about where gold comes from in the universe. So the theory was that gold might come from these events, and all the evidence now is that, yes, this is where gold comes from. We can't make gold or platinum or heavier elements in stars. They come from events like this. So it keeps on coming out with these new discoveries that we didn't really anticipate. I always think after the discovery, it's done now, it's the only way down, but we keep on seeing new and unimagined things. I worked on LIGO for many years, but then there was an opportunity to go and work at NASA. And when I say an opportunity, I heard about this mission, LISA, which was to put LIGO in space, and I did a Google search, I wrote to the scientist, said, I want a job working on LISA, and 2 months later I had a job there. And that was the first time in my career I discovered this amazing thing that if you ask for something, sometimes you get it. I say it in jest, but it really is a valuable lesson. Sometimes you just have to ask for what you want, and don't be afraid to do it. You don't want to do it every minute of every day, but sometimes when things are important, just say, you know what, I'm going to tell someone this is important to me, and you never know what will happen. And this was the first time I saw this. So we've been building this LISA for a long time. This is another mission called GRACE, which is a little bit closer to Earth, and it's using the same technology to measure the Earth's gravity. And what we can do with this is we can actually do a whole bunch of really interesting science about how mass moves around the Earth. And the only way mass really moves around the Earth on a large scale is water. So this tells us where water is, including groundwater, sea level changes, and melting of polar ice. We get a map once a month from this mission, which is with GRACE, which has been up there for about 15 years. And there's another GRACE mission launching soon, which has technology developed here in Australia on board. So I had $5 million from the Australian Space Research Project to work on GRACE, and we did everything, we met all our milestones, we had all this great technology, and we applied for funding to do the next part of it, which is build the hardware that goes on the spacecraft, and then the whole funding scheme got cut. So I had this amazing group of really talented individuals who were mostly from Australia, but some of them had come from all over the world to work with us at the ANU, and suddenly I had no money to pay them. They were all going to drift off to far parts of the world and work for countries that had space agencies, which Australia will have soon. Or they're going to go and join the public service, or they're going to leave science, or whatever. But they didn't want to. They actually really liked working in our group. We had a really great group of people. And so we decided to see if we could take our technology that we developed for these really kind of big science programs and apply it to something else. We'd become experts in a whole bunch of stuff, including this is the space-qualified hardware that we built, and which is now has been rebuilt in Germany and will fly soon. But we decided to do something completely different. We decided to take our technology and start a company. And so that's what we did. So Liquid Instruments has 12 founders. They were PhD students and postdocs and me. And it's actually still got 10 of those people still work for the company now 3 years later, and we're still having a good time. There's been ups and downs and busy times, not quiet times yet, although we're hoping to take a morning off to go see Star Wars when it comes out as our Christmas party. And we decided to take some of the technology we developed for space and see what we could do with it, see if we could apply it to some other areas. And so this is the technology that we'd actually become experts in. This is a special type of computer chip called an FPGA. So if you think about an FPGA, if I try and put it in context, you've all heard about a CPU, which is what's inside every computer, where they can do maybe 1 or 2 or 4 or 8 operations in a single clock cycle because they have multiple cores. Then there's something called a GPU, which is another level of parallelism in terms of processing, where they might be able to do 1,000 things at the same time all across the chip. Well, an FPGA is like the extreme example of that. It can do millions and millions and millions of operations in a single clock cycle all over the chip. So the first thing is they're very parallel and very powerful. The second thing, the name field programmable, means that they can be reprogrammed in the field. You can rewire all the connections of the chip to have it do something entirely different in about 100 milliseconds, a fraction of a second. And the third thing that meant we had a chance at establishing a business around this technology was that they're incredibly hard to program, like really, really hard. Like you need 3 or 4 years experience just to be able to figure out how to get something to run on it. And so we had a team that had decades of experience in this. So this is what we decided to do. We looked around our lab and we said, hey, you know what? A lot of these things that we use, we could actually make with this technology. So every one of these little boxes you see here, it's called test and measurement devices. And every one of these boxes has a circuit board inside it, and it does a different function. They basically measure or generate or condition or characterize electrical signals. And we use them in science, we use them in engineering. Most of your electronic products will use these products to design those products. And it was a big market. And we thought, hey, what if we rip the circuit board out of each of these ones and we replaced it with this FPGA, digital signal processing technology. And the best thing is, because it can be reconfigured, we could replace many, many, many of these instruments with just one device. And so that was our go-to market strategy. We had this idea for this device. It was a test and measurement device with a powerful and reconfigurable FPGA. And the other part of it was that using this equipment really sucked. Like, it really hadn't changed for years. There were these big beige boxes with a bunch of buttons, and they were horrible to use. You had to train people. And we thought, you know, what if we took the best of user interface design, which has really changed a lot in the last 15 years, and we brought it to test and measurement. So we have this great iPad interface. We launched the beta program a couple of years ago with 3 instruments. And then our business model is that when we write a new instrument, we can release it as a software update. And it's like Christmas for scientists. You get this little badge, this little update icon on your app, and you download it for free, and you get a new instrument. We also have this amazingly novel and intuitive user interface, which to really appreciate, you have to have subjected yourself to years of abuse at the hands of existing test and measurement devices. But it really is sort of the crown jewels of the company is the work that we put into making it really, really wonderful to use. So where are we now? Now we actually have 10 instruments. We've updated it every few months. We release a new instrument. Each one of these instruments could cost $20,000 alone, and we release it as a free update. We're out of beta now. We have all these certifications in all these different countries, which we failed many, many, many times. But the team just kept coming back with fixes. We have 5 languages. We now have 17 employees. 3 of those are in California now. And we've been given $2.8 million in venture capital funding to date, which was horrible, and I hate getting venture capital funding, but it's necessary. Really stresses me out. Now we're at the point where we're trying to scale up, and now things are, every step of the company I get scared, and now I'm scared again. So we're scaling up. We have a large manufacturing partner in Malaysia now. On Friday this week, half of the team are flying over there to help with the production. Once we do that transition, it should be okay. We should just turn the handle, and these Moku labs should come out the other side. But there's issues with scaling up that I find very worrying. So yesterday morning, I signed a purchase order to buy 10,000 power cables. We sold 200 devices in the history of the company. And now I just bought 10,000 power cables. I'm sure that we'll get through them one day. The great thing is that we now also have a lot of help. So we've signed up distributors in 27 countries now. We also sell directly to most places in the world on our website. So that's all going really well. And the one thing that gives me hope that one day I'll have to stop going back to venture capital guys and asking for more money is these are our sales since March. So these are our monthly sales, and you can see that it's heading in the right direction. Clearly, it's just going to keep on going up and up and up forever and ever and ever. But it is scary, and it's exciting at the same time. I think a lot of the things that people have said earlier today really have resonated with me, and the one about believing in yourself is really, really important. I've never been so scared of anything as I was of starting Liquid Instruments. And I was a tenured professor who could just put my feet up and run out the clock for the rest of my career, waiting for the ICU release of death or retirement or something. But I want to do something interesting. I want to do something that had impact, and I think that's a really important thing, is to do something you believe in. In science, for probably a few decades, we've been a little bit obsessed with publications and now citations, but really, you want to do something that has real, genuine impact. And this is something that I could tell my grandmother about, and she kind of gets what I'm doing now. And so I find that really satisfying, and that makes for a happy career. And surround yourself by a group of people that you like and you have common goals with, but they are not all the same as you as well. You need people who will challenge you. So I think the one thing that has surprised me most about this whole startup journey, I guess, is just how helpful people are. I kind of thought the business world was like a dog-eat-dog world where you had to keep everything secret and everyone was trying to bring you down and competing with you. It's really not like that at all. Everybody has been amazingly generous with their advice and with their time. Sometimes that advice is not the best advice, but it comes from a good place. So if you do decide you want to go this path, there are a lot of people out there who can help you along the way, and it's important that you get that help because it is really challenging to do by yourself. And for me, I have times when I just really doubt myself, and even today, what we're doing, and it's only because of those people around me who are there to help pick me back up again when we have a bad day that it makes it possible to get through it all. So I think I'll leave it there. Thanks very much.
Right, do we have questions for Daniel? I think the lady up the back there, because I know she had a question earlier, she wasn't able to, so.
Two tiny things. So you don't like science, but you did physics for 21 years.
I like bits of science. I do. So I enjoy the challenge. I'm a competitive person, I think, and so I like just, problem solving. I think is great. but I am quite selective about the stuff that I'm interested in, and my eyes do glaze over a lot of the times when I go to talks.
So my second thing was, what do you think was like your biggest fallback, and how did you like bounce back from it, or what was the lesson that you learned from that?
So probably the lowest point in my career was I was working at NASA, and I promised my wife that we would only move to California for 1 to 3 years was the plan. And at NASA, everyone was so supportive, and they had great mentoring there that I'd never really been exposed to in the past, and everything was going great. They paid a lot of money, they gave me a permanent position, but we were not happy over there. We wanted to move back to Australia. We had 2 small kids that we wanted to be close to family, and I couldn't get a job back in Australia. It was really hard. And every year I would apply for fellowships, and every year, the way you find out in Australia you didn't get a fellowship is you don't get like a letter from the Prime Minister saying thanks for applying, but you didn't get it. You find out by reading a list, and you get to the bottom of the list, and then you turn the page over, and it turns out there's no back page. Like that's it, that's the one page where, and if your name's not on it, you kind of go, oh. And so I applied for fellowships for 3 or 4 years from the US to try and get back to Australia. The way I ended up getting back is I actually applied for an ARC grant with a colleague. We got the grant, but they only gave us 30% of the money. So I could take my name off the grant and be paid as a postdoc for 30% of my time. And so I said to NASA, this is the second time in my career I asked for something, and I said, hey, I'm going to move back to Australia, but you're still going to pay me. And he said, okay, that's fine. So for the next 5 years, they'd never done this as far as I know. For the next 5 years, I worked 70% for the Jet Propulsion Lab and 30% for the ANU, and I would commute back to Pasadena and live in my neighbour's back house. That was a tough time, but yeah, it was the leg up that it gave me to get a grown-up's job back in Australia. But it was quite demoralising, and I see that everybody goes through this. It is quite sad, the success rate of fellowships and things like that in Australia. But what I do see also is that good people can find a way, and you shouldn't. If I look back now, I was always worried I was about to get fired, and I think, maybe I shouldn't have worried so much about that.
Do we have any other questions? Down here.
I just wanted to ask, while you're looking at black holes, did you ever get to see the phenomena of spaghettification?
No, and I've always heard my 3-year-old nephew is obsessed by spaghettification.
Me too,
as
don't
well.
worry.
Oh, really? Okay. No, it's very important. So that'll probably be the next major discovery. That's got to be a Nobel Prize in itself for spaghettification of astronauts.
For those of us who don't know what spaghettification is.
Do you want to explain what spaghettification is?
I'm thinking like pasta, so, you know.
It's like a combination of an astronaut with pasta getting stretched.
String theory. No, it's not
string
theory.
It's because near a black hole, the gravity is super, super strong at your feet, but slightly less strong at your head, that your feet get stretched, and it just gets worse and worse. Yeah.
Okay, so I shouldn't have asked that one. Do we have one last question? Obviously, your presentation was just awesome, and they're still awestruck.
Thank you very much, Kate. Thank you. All right, thanks very much, guys.
So I think a big take-home from that one is don't ask, don't get. And frequently, as women, we don't ask. We hope that someone will just appreciate the hard work we put in, and they will notice us, and they will suggest promotions or whatever, and it doesn't work that way. So don't ask, don't get. Think about it. The worst thing that can happen is someone can say no or not now, okay? Morning tea. Morning tea is on. Everyone knows where morning tea is.